Jodhpur at electrical department.
Okay.
I'm also doing a BTech project under Vinod sir, and we are working on implementation of FPGA and AI models onto them. So we are working on attacks and hardware robustness of the models. So
Great.
my interest is on this, and I also went to Japan for an internship for AI
Mhm.
engineer intern at Otsuka Corporation, a company
Mhm.
which has a huge IT and sales department. And I was there for making the AI systems and the generative AI architecture for them.
Very good. Perfect. I am also, in Jodhpur for almost 10 plus years. I did my 10th class from there, from KV KV Air Force number 1, which was, just near the Polo Ground. And
Mhm.
I think this is the MGM is converted into ITI, right?
So MBM was our previous campus. So after that,
Okay.
we got the campus and we moved to
Okay.
IIT Jaipur.
Okay. Perfectly fine. Yeah, I'm aware of, because I was, in 9th class, I think usually I'm going to NCC office. NCC, ground and all. So the main gate of this MGM was just in front of that. So I'm aware of all those. Long time now. Okay, great. I think we can start now. We have good numbers. Professor Ajay, if you can permit, then we can start.
Yeah. So I think welcome for this session, and I thank NXP for doing this session jointly with IIT Jodhpur. And as I learned from my students, they are very eager to work, and many of our faculties also would like to work in the related or complementary technologies where we can work together and contribute for the society as a large. And as I mentioned, our department, E department, offers 9 specializations also. So we are the only department offering so many specialization, because all the electrical electronics part are there. And these are for our BTech students to take these courses in specializations, and they can go away with a degree in a specialization branch also. And to name these are like 5G and beyond communication, signal processing and interpretation, cyber physical system, nanoelectronics, and quantum devices, VLSI system, smart grid, artificial intelligence of things, and engineering innovation. So these are the 9 areas. Engineering innovation is one specialization which is a unique feature, where a BTech student can do a semester project in an industry. So it is a part of the curriculum, but they can work on a project at the industry, either going to the industry or here working from here. If remotely he can work, or partially he can go. So whatever way it works, but he has to take a supervisor from department also, because it is a course which is evaluated by the supervisor at the end of the day. So this is a very special kind of specialization we offer, which we call engineering innovation. So we encourage our students to take up this specialization and work with the industry for an entire semester on some innovative problems. So this is about E department, what we are offering at this moment at IIT Jodhpur. And I thank all the colleagues, all the eminent speakers who have joined from NXP side to speak on this one and give a fair idea to our students what are the possibilities there, and how they can exploit a company like NXP's expertise for their growth. So thank you very much for connecting today with us, and please proceed for the further discussions and presentations.
Yeah, thanks a lot, Professor Ajay, for giving us an opportunity to share IIT Jodhpur platform. NXP India. In India, basically, we are operating from 4 locations: Noida, Mostly, we have almost 1200 plus here engineers here. Then from Bangalore, where approximately 1700 plus. Then third location is Hyderabad, and then Pune. So Hyderabad is more of 5G related enablement, all those things, mainly software center for SC division, which is basically the edge processing. And then all the connectivity related stuff, we are in Pune, so we are close to 250 plus there. So almost if you calculate all NXP India engineers community, which is close to 3,500 as on today. Hitesh Garg is our a dynamic leader, vice president, and India country head. He is having very different ideas, how to support, how to enable uh, the technical universities in India. So we started a lot of innovative platforms. One of this is the this Campus Connect sessions. So every first and third Tuesday every month, we are running this sessions. The same link, same time, anybody can join us. There is no restrictions to anyone. So as much as students can join, they can learn new things. The only thing is on first Tuesday every month, we are mostly taking VLSI related topics. And on third Tuesday every month, we are basically taking up the system engineering topics. And today we have very important topic, which is V&V, and this is basically the verification and validation, pre-silicon, post-silicon. A lot of stuff is there. We have two our experts, which is visible on the screen. Mr. Amitav, he is with NXP for a long time now. He is our expert from the verification side, and he is having 70 plus years of experience. Maybe he can introduce himself later when he's going to start his presentation. We have very senior and expert from the emulation, SoC emulation side, Mr. Gaurav Jain. He is basically the director of this group, and he is also having long experience, plus 15 years of experience in NXP only. So yes, we have experts here who is going to share their experiences, and NXP India is very committed to support the university campuses, and we are running a lot of programs. So you can most welcome if you are close to Delhi, please visit our Noida, and if you are in Bangalore, you can visit Bangalore office. We can arrange all the related stuff to introduce what NXP is doing, and we are also running some collaborative programs also. For yes, I'm not going to take much time here because students are waiting for the very exciting session. This is a very important journey during the SoC development life cycle. So without investing or much time onto the introduction part, I'm going to hand over to Mr. Gaurav, who is our expert from the emulation. So he is going to sail through today's presentation. So over to you, Gaurav and Amitav. Gaurav, unmute yourself.
Yeah.
Yeah.
Thanks, Manish, and thank you all the professors, Professor Ajay, for enabling this and allowing us to proceed. So I think uh, just a brief introduction on my side. So uh, I'm Gaurav, and I have been with NXP since 2008, so more than 15 years, and I think overall, I have around 18 plus years of experience. I did my engineering from IIT BHU, Varanasi, and I worked in different domains. Started with IP design, verification, have led multiple projects in SoC verification, worked in low power verification, and currently I'm looking into SoC emulation domains. So I think on behalf of NXP, I welcome everybody, warm welcome to everyone, and hoping to that this session gives you a good insight into what we are doing and how we are doing different what are different areas that we are covering in these domains. And Amitav, I think if you also want to introduce yourself.
Amitabh, unmute yourself.
Thanks, Gaurav. Hello,
ahead.
everyone. First of all, it's a great pleasure and privilege to be giving this talk to all the students. And thank you, IIT Jodhpur, for setting this platform. So one interesting aspect, as Manish told, it is on the first Tuesdays where we deep dive into the VLSI part of it, which means pre-silicon. Pre-silicon is something wherein the application space is not yet there. The silicon is there, and all the hardware connections, and you need to maintain all those stuff to gain. So the topic you would probably see why we have written AL/ML usage. So it is more like adaptive learning and machine learning usage. It is a step wherein we see how we can adapt to the ongoing requirement, the Moore's law of semiconductor VLSI, and how verification needs to scale. So the content would be shared between myself, Amitav. So I'm the verification manager over here, having around 19 years of experience and 17 years of experience in NXP alone. I have worked on verification architecture for different MCUs and MPUs, and my specialization is on low power chips. So based on that fact, I think I'll take the first half of this presentation, and then moving on to the agenda. Okay, so the agenda would start with pre-silicon experience. What is dynamic? What is static? How industry is viewing the pre-silicon verification. Then the verification methodology. Where are we spending our time? Where is the need for those adaptive or slash machine learning in our domain? Bugs. Bugs are coexisting with features. We cannot say that we are zero in bugs. Whatever tests you do, how many thousands or say millions lines of code you execute testing it, there would be a corner case which would be there. And that needs the specialized learning or the machine learning kind of experience to get to the a zero defect or a zero bug kind of architecture. And then how a bug analysis should move towards a bug avoidance. And that is where the ML way or the machine learning way will kick in. So the next part, SOC emulation, would be taken care by Gaurav, wherein he would introduce us to emulation, the needs, why it is, how it is complementing the simulation world, and how typical SOC usage of emulation is there, and obviously wherein the artificial intelligence and machine learning is helping in emulation and prototyping. So overall, we plan to cover it in 50 minutes of time, and post that we'll take any question answers. And also we would want, if any questions are there, you can write on the chat window if you have any questions over there. Okay, I think let's get going. So this is a very standard and way of defining what a VLSI or a semiconductor or an ASIC verification looks like. It is very standard. If you look for any EDA vendors, any chip manufacturer, you will find this as very common. So you can broadly classify verification as static and dynamic. Dynamic is something wherein you are pushing your stimulus, you are making your stimulus to verify the DUT or the device under test. Whereas static is something wherein the mathematical algorithms are used to check how the state space of your machine or your DUT can be checked. So this is a very broad or a broad level, a 10,000 feet idea of how to strategize a verification. Within that, we have for statics, we obviously do code reviews, code analysis, and a formal tool, which is EDA supported, which again works on mathematical connotation, and it forms its own vectors and verifies the DUT. So this is a very important thing to note, that formal is based on the vectors that it creates while analyzing the DUT. Similarly, on the dynamic side, you would have the simulation, which is while you are using the EDA vendor tools to simulate the design before it goes into the post-silicon phase, wherein the chip is or the manufacturing of that design is done, and the prototyping part, wherein you would do emulation or FPGA prototyping, or the silicon where you would run the software. Within simulations, again, there is a point wherein the formal and simulation can coexist, which means that there could be certain scenarios wherein the formal cannot be exhaustive based on the state space or the size of the DUT. So what you generally do is you take that DUT into one known space, which is a state space wherein it is not exploding, or it is rather exploding beyond that. So once you reach that state, now you want dedicated dynamic test cases or simulations of those test cases to get to a logical conclusion or to find the health of your DUT. So this mixed kind of approach are also very, very keen, and this also bridges the gaps that can be there between a static and a dynamic way of verifying it. So within formal, there are different ways wherein you can do an equivalence checking or a model checking, or you can prove the properties using that formal way. So this is a basic verification framework or methodology / architecture, which any VLSI company would be following. Now it depends on the type of chip that they're doing. They might tick box few, they might leave few, they might add certain things on top of that, but the basic infrastructure or the backbone would be based on this. Now moving to this next slide. So how the previous thing is moving into developing a verification methodology. So this is a busy slide wherein you would on the left column, you would see the verification flows and steps, how we go with time with respect to verification. The middle block will tell what kind of methodologies which is prevalent and what kind of work or tasks are getting done to achieve that. And to further substantially add to what this can help, or what are the bottlenecks, or what can be the positive inputs to this, the comments are there for the commentary for that. So if I go on the left side of it, the feasibility study. So once you get the architecture or the chip that you have, you would always have an architectural document based on what that chip does. So a study is required to understand or do your verification planning, how you want to verify, what part of it would be taken by formal, what part of it would be taken by simulation, what is left for emulation. So all those things needs to be done there. Now, once you strategize that, you would go into the next setup wherein you are adding the V plans, wherein you are adding what kind of tests, what kind of coverage, what kind of end product, what kind of traceability to the architectural document you had would be taken up. Now, once you have done the strategy and the planning part of it, you would now architect the test bench. So this is the first of the execution work. When you would start working, you would write the code on system verilog / verilog with anything like a UVM kind of thing, which would act as a backbone for your environment. So this is a repetitive cycle. So once you get there, then you will start writing your stimulus. You will understand the use case for the customer. You will modify the stimulus, and then you will take it to a regression management. A regression is something wherein you are running a bulk or a chunk of your stimulus to stress the design and it runs one after another. It's not that you are running it one by one after finishing. So you parallelly run so as if a standard, say 90 nanometer chip used to have 2000 test cases. Now a 5 nanometer chips would have 10 to 15,000 test cases. So to run them, you cannot wait for one of them to complete and then start another. So therein, the EDA provided regression management is helpful. And obviously, how do you comprehend that your verification effort is done? So the metrics to it is coverage. What is your coverage target? Is it only toggle, or you are covering some of the blocks or the expression which is there in the RTL? How you are covering that? Are you adding cover points specifically, or you are adding some assertions to check whether that state machine has taken the point from point A to B? What are the states that the state machine has traversed? So those needs coverage collection view, which you would always want to maintain with regression. So once you get those data, you would always do and analyze the coverage. You will find some gaps. You will again go back to stimulus and use cases. You will find that some of them, there are three ways of doing. Either you're covering it. Second, you cannot cover. So you need a disposition, or you would exclude those because those are not relevant for that duty. And the third one is there is something which could be covered by some specific corner case wherein you need to use some of the industry methodology like the formal plus a dynamic or specific dynamic cases to cover that whole. So once you are done, so you would also want to check how good was your test bench, whether you are overdoing it. You also can optimize your test bench with respect to an example would be if 5,000 test case can achieve 100% of coverage, why not see and look for it if the same can be done, say, in 4,000 test cases or not? So those kind of qualification is an aftermath, wherein you would be always looking to have continuous integration and continuous development, which means that you are optimizing not only your DUT, you are also optimizing the duration or the life cycle of your project and also making your test bench leaner or more relevant to the bugs. And then obviously you need to sign off. You need to sign off on all test cases running. You need to sign off on test bench qualification activities. Also, you need to sign off on coverage. So based on all these things, where do adaptive learning or machine learning can help? So if you see, there's a cyclic nature, and the industry data that shows, which has been year over year or decade over decade, I would say rather, that most of our time, which is typically 40 to 60% of the time, is within the three box that we are highlighting. It's a circle. You have test bench, you have written stimulus, you run regression, there is coverage fallout, you go back, you again tune your test bench, or you redevelop your test cases. So this takes up around 60% of your cycle. So the idea is how to have the debug triage, which can help, or the adaptive and machine learning, which can help in reducing this cycle. So this is the high level topic wherein the verification methodology or the debug triage can help in achieving this kind of goals. Moving to the next. So how a bug is seen? It's a very simplified form. Though at the top, seeing this picture, you might see that there is a short between the two outputs, but it's a black box for all of us, correct? So it may not be so much intuitive that while seeing this kind of a design, you would be able. So what you will do, you will select random stimulus, which would be driving all the inputs, and the important part to it is, if you see the leftmost side, it is n cross, which means you need to repeat this pattern n cross time to see if there is a bug, which is probably visible once you run that. So this is very expensive method. So, and this is prevalent. So if you see 10 years back or 15 years back, this was the way wherein the smaller SOCs could live with that, wherein you had 500,000 or say test cases in the scope or range of 2000. You can always limit that. The runtimes were in say 40 to 1 hour, wherein you can run the entire simulation and get the results in 1 hour. Now this has gone to 3 days for some involved test cases. So you don't have those time to repeat NX for this to find this bug. So what is the key takeaway? The key takeaway is, though we're shrinking our nodes, we are going from say quarter micron to 90 to now 5 nanometer or say 2 nanometers. Bugs are reality. And the cost of finding these bugs are proportional to the advancement of tech nodes. The higher you are in the tech, or the lower you are in the tech nodes, the cost of that single bug would exponentially rise. So if you see a bug which was found at the same stage in say 10 years back is much costlier, which is like 3 to 5x costlier. The same bug if you find it in a and the similar 5 tech nodes or the lower nodes. Now, the second is the bug trend. The bug trend is moving from parts per million bugs to parts per billion bugs. So all these smart cars, the Teslas, the BMWs, they're looking for so much advancement in our automotive industry where everything is now driven by semiconductor content. And one of the requirement for this automotive market in special is that your number of bugs should be in billions. The reason behind is very simple. You cannot afford to lose life because one single bug in your car, correct? Just think of yourself. You're driving a car and your uh, adaptive braking system is not working perfect due to one of the bugs that is demonstrated on the top. This is catastrophic. So we need to, in spite of having the advance in technical nodes, the rate of finding the bugs needs to be elevated so that we are finding more bugs ahead of the silicon. And obviously, with so much competition, every customer or every silicon vendor would require a very shorter runway with a challenging time to market. So everyone is competing for that slot. So these are something which mandates how we should go from our historical way or the orthodox way of finding bug analyzing to a bug avoidance, wherein the adaptive machine learning way is kicking in. So what is bug analysis parameters? So as I told, time to find a bug. It has changed drastically. Reproducibility. Some of the bugs we have seen, I think Gaurav and me can vouch, we have found a bug which takes days to reproduce because the exact scenario where all the inputs are touching because of the randomness of the design or the verification test bench takes days. And it has happened. It is improving, but it is still a big factor in bug analysis. Recurrence, which is also a point wherein a bug introduced, say, in the earlier part of design because of some malfunctioning of some tools or some human mistakes can get reintroduced in a very later stage when you're about to tape out. So those kind of analysis needs to be correct by construct. We cannot wait for them to be found via our traditional way. Fix and prove. This is something which is a job of the verification engineer, wherein we are not only finding the bugs, you are also helping the design or the front end or the RTL team to fix it, and then you prove it back. Okay, this is the fix that you have provided, and this is working okay. And this is not only for your only one test case which failed. You need to again run the entire regression to check whether there are any orthogonal issue which cropped in because of that fix. Root cause analysis is something which is very much mandated so that everything is correct by construct. You cannot rely on a judgment of an engineer to find a bug. It has to be correct by construct, and this is how a ML way can help. And obviously, there would always be external parameters. Your regression, common code in regression, someone changed it, someone who is co-working with you, a human mistake crept in. Some of the randomization data that I told took days to converge on those. So these are the typical analysis which we started, say, 15 years back or 12 years back. Those are relevant, but we need to change the ways. We cannot rely only on this kind of method to do it. So what's the next way? The next way would be on this three important avoidance way, which is triaging, bug triaging. How are we classifying the bugs? What is important? What is more effective? We need to find it. Predictive detection, regression data. We have you can say gigabytes of data which is getting dumped as a regression from regression database. We need to analyze them to have an adaptive model of predicting the next bug whenever there is a new release. And easy access, obviously. So for there are something which the machine can do, correct? So we need engineers. Otherwise, our job are there to understand what the machine themselves also can't do. So based on that, we need those easy access wherein if there is a failure, how easily those 2 to 3 days of runtime needs to be under an hour or say hour or two, wherein the engineer can get all the data, all the log files, all the web forms which is required to do the thing. So again, this cannot be done via an engineer. It needs the machine to be doing it for them. So now going deep into how it is the ML way of avoiding the bug. So bug triage. Bug triage is mainly on clusterization. So you need to see what is the cluster that this is fitting into. So you make buckets. You cluster based on similar kind of bugs or say dissimilar kind of bugs. The cluster can be any which way. You need to prioritize. For example, you are seeing that a bigger chunk of data is because of something which is failed with one cause, which is causing a major fallout. So you need to prioritize, and the machine learned model needs to tell you that this is the cause. These are probably the 5 causes wherein your 70% of test cases would be fixed if you can do the right prioritization. So this is how the next trend of debug should look like. The third one would be root cause analysis correct by construct. I think I touched it earlier as well. This is very much required. With the number of nodes, the number of transistors increasing, it cannot be humanly possible to check all those connections, even if you have say months of time. So both pressing parameters are the reduced size of your or the increased size of your transistor and the lesser time to market, which tells us that it needs to be correct by construct. So what's the predictive detection? So predictive detection is something which the ML or the adaptive, I would rather say the adaptive learning would tell that regression data, the common mistakes are there from your previous log files, and this is where it cannot go wrong. A very easy example is the tie-off. So often we see that the port of the RTLs are tied off in a wrong value. So this is a very, it takes believe me, it takes the entire cycle of running the test case, generating the dump, analyzing it, getting to there, takes one full 24 hours of human runtime to do it. Vis-a-vis, a predictive data detection can reduce it in, say, in sub-hour, like 30 minutes or 45 minutes kind of time. So we need those kind of predictive adaptive learning. There are many cases where a warning is issued by the simulator or an error is issued by the simulator, and in some cases it crashes with a fatal. So we need adaptive way of changing there as well, wherein if a warning is causing or doing a majority of your test cases is facing the same warning, it should be adaptive enough to do it or elevate it to an error, or in certain cases a fatal, wherein you are mandating that please have a look at this warning. It is causing something which might cause some issues. So this kind of adaptive learning is something wherein the the EDA vendors would also want to work on. And obviously the cone of influence. So once we get to a bug, we always trace it back. What is the source? We find the source, we fix the source. But it needs to be the other way around as well. If that bug is propagated, whereon it can cause a failure. So based on that, your cone of influence would decide the fallout, the regression fallout, or with help the left column of bug triage. So this is something which is very important, and this kind of adaptive learning is the scope for doing the sub 10 nanometer chips in some record times, which all the giants are trying to achieve. Now, once, as I said, there's something that the machine can do, but what the machine can help here is having an easy access to whatever we have. So as an engineer, I would love, once I reach morning and open my desk, I have an email stating that last night regression, these are the fallouts. You have 10 test cases. These are the 5 possible reasons. This is the dump and this is the log file with highlighting that these are the possible anomalies from your last run. So these are the things that we are striving for whenever we have those targets in mind. So this is wherein a generative regression is I coined this term generative regression because this type of generation of all the data which would be easily accessible to an engineer would be the next eureka movement for say a verification debug engineer. Similarly, randomness to exact replication. So as I told, in our times, we used to take days to understand the randomness. Now it needs to be hours to get to that kind of root causing or pinpointing. Log preservation, waveform availability, I touched about it in my first point itself. And obviously the predictive state space convergence, which means the data that you have shown or the data that the machine has learned through should be able to give you the exact number of test cases that you need. For example, you started with 10,000 test cases, but during, say, after 2 months of operation, the machine should tell you, okay, your similar results can be achieved by this 200 test cases. So this is the state wherein the bug avoidance can help, and this is the future wherein the VLSI domain should be looking at for all this faster turnaround time. So just to conclude on my topic here before I hand it over to Gaurav, there is no one step. We need to take stepwise. We cannot jump over here. We cannot jump the queue. We need to take step by step, but simple data quenching and all these 3 would take us to the level wherein we would be able to manufacture those chips much faster than it. Now, giving it to Gaurav to give you the next level of the you can say the friend of simulation emulation and how it can take forward. Over to you, Gaurav.
Yeah, thanks, Amitabh, for the very insightful session on AL or AI/ML usage in simulation world. So, so I think as Amitabh mentioned, guys, uh, it is very important that in the current set of SOCs, which are very complex and the design size can go up to millions of transistors or gates, hundreds of millions of transistors or gates. Uh, and we need to ensure that all the different IPs or components in a system on a chip is interacting with each other correctly and functioning together. So verification, or I would say functional verification, is the very critical component or the critical function of the overall design flow, as it ensures that the design which is getting developed is meeting the specifications, and uh, we meet customer requirements, uh, and it ensures that we verify that the design is behaving as per the required specifications. Now, for functional verification, there are multiple techniques, as Amitav also touched upon. Simulation is the most popular technique we have. Within simulation, we have dynamic, formal, and then we also have emulation, right? Which is another technique to ensure that the design is robust and working correctly. So I would be covering slightly also on what is emulation, how it is different from simulation, and why do we need emulation before covering some of the areas where AI/ML can help in speeding up or accelerating emulation activities further. Uh, I think AI/ML is one of the niche technologies, and all the companies, including the tool companies, which we call as EDA, they are putting in a lot of focus and effort in enabling solutions or tools, or working on different tools or flows where we can leverage AI/ML that can help in the overall design process, whether it is design, verification or backend. So there's a lot of research ongoing to identify the use cases for AI/ML in the chip development. So this is basically an high level overview. So maybe let me start with what is emulation. So emulation is basically a process of uh, prototyping or mimicking the design behavior on a piece of hardware, uh, so that we can run that hardware logic on that emulator. So typically, the simulation is running on a server or different cores on a server, where the design behavior is mimicked on a software simulator, and the different and it is basically running in a serial fashion. Whereas on an emulator, the different design components are mapped on a emulation hardware, and since this hardware logic can compute the different functional logics of the circuit in parallel, uh, so it runs much faster than the simulation, the software simulation. So basically, emulation is the process of mapping the RTL design or the actual SoC design on a piece of specialized hardware, where we can download that particular design and emulate the behavior of a design similar to how it will behave like once it is fabricated and the silicon is available. So this is basically what we know as emulation, and what is the basic difference between uh, simulation and emulation. Okay, so why is emulation needed? So basic fundamental of why emulation is needed is over on top of the other techniques like simulation and formal is the speed up or the acceleration that it provides. Uh, there are multiple set of scenarios where sometimes simulation or formal techniques can fall short. For example, if there is any embedded firmware in the design, and we need to ensure that the firmware or the software is are working correctly along with the hardware logic, then typically we use emulation platforms because it is very time consuming to run firmware or software in the simulation. So I'll cover some more details on that, but that is the basic advantage of using emulation. It provides you the speed up or the acceleration, which is much higher than what we can run in the simulation in a specified period of time. Uh, we can run test cases with real world uh, targets. For example, we can interface with an actual Ethernet exerciser or a packet generator, or we can we can run with an actual debugger, which is being used even in the post silicon environments. Uh, Obviously, we want to catch as many functional issues or bugs in the pre silicon phase, uh, because anything which is going beyond logic freeze or beyond silicon is very costly. So these are some of the areas there where we need emulation on top of what we are doing in simulation and formal. Uh, there are typically three most popular set of emulation hardware that is provided by the EDA vendors. We have Cadence Palladium, Zebu from Synopsys, and Veloce from Mentor. These are the three popular tools, and then we also used the off-the-shelf FPGAs from Xilinx or other vendors for FPGA prototyping. Okay, so again, just to highlight, emulation is 10 to about 5 times faster than simulation. Uh, it basically mimics the board level environment or the real world environment where the silicon is going to be used. Uh, any use cases which are long running, or where hardware firmware co-verification is involved, uh, those are more suitable for emulation because of the time needed in the simulation world. Okay. So coming to a typical emulation use cases. So obviously, along with the functional verification of the design, these emulation models are also used for by the post-silicon validation teams to enable their test cases or content before the silicon is available, so that they are ready for running their scenarios on the actual silicon. Uh, Most of the software or application teams are using the emulation models to develop the software. Uh, Also, the embedded firmware like the boot firmware, etc., is which is burned in the SoC or in the silicon, that anyways need to be developed before the logic freeze and tape out of the project, so that we have that boot firmware available, and we need to ensure that it is working correctly with the hardware logic. uh, any debugger logic or third party software, like for example, typically we are using debuggers like Lauterback or ARM-based debuggers. So those software needs to be developed again. That is being done on the emulation platforms. Okay, these are the different use models of the emulation and the different performance that can be achieved with different models. So on the left hand side, on the vertical axis, you can see the typical emulation speeds, emulation model speeds that we are able to achieve. Obviously, these are increasing with the advancement in the tools and the maturity of the tools. Uh, so as you can see, the simulation is running around 100 hertz to 150 hertz, right? Because it's a software-based simulation which is running on a core and it is event-based. It is serial in execution, so the speed is the lowest. And then on the right hand side, the highest is the in-circuit emulation, where basically we are mapping the design and test bench both on the emulation hardware, which basically means that all the synthesizable component is mapped on the hardware, and we are using real world interfaces like actual physical debugger or a Ethernet exerciser to interface with the design and verify that it is working functionally as per the real silicon. Uh, so I think most of the most common use model that is currently being used is transaction based acceleration, which is the middle one, where we are having both the speed as well as the control and debuggability. That is the feature of simulation world. So it is like best of both the worlds. Okay, so slightly some more details on these use models. So as I was mentioning, the ICE mode, which is basically the in-circuit emulation, this is the fastest, and here basically on the left hand side you can see these are the emulation hardwares and we are mapping the design. So by mapping the design, I mean we are synthesizing the design into an and compiling that netlist onto an FPGA and generating a bit file that can be downloaded on the FPGA. So that is basically the design is what is meant by the design mapped on the emulator. And on the right hand side we have the different for example, in this case, we have the Ethernet traffic generators, which are the Ethernet testers, and they are interfacing with the emulator using the speed adapters, or we also call them as speed bridge, because the emulation model is working say around 2 megahertz speed, whereas the Ethernet testers are working at a higher speed. So we need speed adapters in between so that both these hardwares can interact with each other uh, correctly. So this is the fastest mode of emulation model use model, and it is also most expensive, and it is dependent on a lot of hardware and lab maintenance is required here. Okay, coming to the other one, which is currently in industry, most widely used, which is basically transaction based acceleration. So in this case, we are basically mapping our design as well as the external VIP or the verification IP, or in this case, we call them as accelerated VIPs. So the functional bus model of that external protocol is synthesizable, and that is mapped on the emulator along with the design. And then there is a software layer which is running on top of this BFM or the bus functional model, which is running on the host machine. So this way, we are not dependent on any external hardware. We are basically using virtual or the software representation of the different protocols like Ethernet, PCI, or JTAG for debugger. etc. And this is more closer to the simulation world, wherein we can generate or write test cases to generate different kinds of traffic or data that can be driven on the DUT pins to excite that interface or those interfaces in a concurrent way. So this is currently the most commonly used approach. Okay. Some of the prerequisites I'll cover. Will not be going into a lot of internal details, but I think as I mentioned, one of the prerequisite is whatever we are going to map on the FPGA or the emulation hardware, it has to be synthesizable. So some of the you know uh, constructs which are used in RTL or test bench may not be supported on the emulation hardware. So for example, forever, trans, all these kind of primitives are not allowed. We need all the UDPs to be synthesizable. All the memory models which are used on the SoC, whether they are in-house or third-party memories like ARM, etc. We need to use the synthesizable models. And typically, all the analog components, we are either using synthesizable representation if possible. Otherwise, we are typically stubbing the analog components. By stub, I mean basically there is no functionality maintained, and only the outputs are driven to a safe value. Okay. All the clocks typically in the simulation world, we are driving the clocks from the test bench. On the emulation side, we are driving the different clocks from the emulator clock source, and we need to know what all are the primary clock sources in our chip, and what are the relationship between the different clocks, what are the different clock divider values that we need to use. So all these clocks are then driven from the one single emulator clock source. So that is basically on the clock side. We need to also model, different pull up, pull down requirements as per the protocol on the emulator. Uh, if there is any multiple functionalities on the different pins of the SoC that are merged, then we also need to model that in the emulation test bench, so that multiple drivers can drive the DUT pins as per the functionality that is selected at a particular time. Okay. Uh, Emulators are generally two-state, only 0 and 1. There is no concept of four-state here, X or Z, though some of the recent enhancements are uh, working on enabling four-state simulations on emulation as well. Okay. Uh, so typically on the from the external interfaces, like if there are any DDR memories or flash memories that are being used as part of the test bench. So in simulation, we are using the behavioral models of these memory components or external components. On the emulation side, we are using the synthesizable models of these different memories, and they are provided either by the EDA vendors or from the third parties from which we are procuring these memory components or other components. Okay, so these are obviously required so that you can mimic the test bench around the DUT on the emulator. Okay, these are the examples of the speed bridge. So I think this is related to the ICE mode, wherein if you are not using a VIP, instead you are using an actual physical component to connect to the design on emulator, then we need to use these speed bridges, which basically do a rate adaptation to so that the faster physical components can actually communicate with the slower running emulation hardware. So typically we have all the speed bridges available for standard protocols such as Ethernet, PCI, uh, and all the other standard protocols. We have those available. Okay, so just to have the right expectations from emulation, I think it is more required for the validation of the digital blocks, because we are mostly stubbing out the analog or replacing them with a miniature representation. There is no concept of SDF or timing delays, so it is purely RTL based simulations. Uh, yeah, you might have heard of gate level simulations, so there is no concept here. For that, you need to use the simulation only. Speed bridges are available for limited interfaces, the standard interfaces only. So if there is any proprietary interface, then probably speed bridges are not available. Uh, Emulation models are slower as compared to FPGAs. By FPGA, I mean uh, if you are mapping some small piece of RTL design or logic on a FPGA, using Xilinx FPGAs or off-the-shelf FPGAs, then it is slower. Emulation is slower compared to that, and obviously SoCs are running in megahertz or gigahertz speed, while emulator is running at probably 2 to 3 megahertz range. However, it is much faster than simulation, which is running at 100 or 50 hertz. So from that perspective, it is much faster. Uh, then, as I was mentioning, every clock is derived from the Palladium, from the emulator clock, that is the master clock, and all the other clocks are driven or generated from this master clock based on the frequencies. Okay, all the clocks are relative. All are synchronous clocks generated from the same master clock. Uh, and again, this platform is not used or not a replacement for functional verification. It is basically, this platform is used to complement or supplement the functional verification uh, on the areas which are not possible to run in simulation world because of speed, because of real world targets, because of software co-verification, uh, and long running vectors which are very time consuming on the simulation world. So this is a high level emulation flow. We basically synthesize our design and the test bench, basically the synthesizable component of the test bench. We compile the pre-silicon model, generate the bit file, and download it on the emulator, and then we run that simulation on the emulator, and any issues if there during the bring up, we can debug either via JTAG debugger, or we can dump the waveforms as well. Or there are also tarmacs which can be used uh, to basically debug on emulator. This is a high level test bench diagram of an emulation test bench. Okay, so in the design, we have the design SoC. In the center, we have this SoC design, and then outside we have the different bus functional models, for example, MIPI, or different protocols, I2S, etc. And these bus functional models are synthesizable, so they are also mapped on emulator. And then there is a C or C++ layer which is running on top of these BFMs that can be configured by the user to generate different kinds of traffic. We can also use a speed bridge to connect to an actual physical component. So just an example of how complex this test bench is, and what are the different capabilities that you have here. And then I think another real world examples of where you can use emulation is if you are basically developing some vision processing or radar processing SOCs, then if you want to process an entire image or you want to process a full radar sample which is having say 256 chirps or maybe 512 chirps, then that is not possible to run in a reasonable time in the simulation. So typically all these use cases are targeted on the emulation platforms. uh, Similarly, some of the performance benchmarks, again, these are very long running scenarios, uh, are again sweet spot for hardware based or emulator based verification. Okay, so I hope this had given you some idea about what is emulation and uh, how it is different from simulation, what are the areas where we can use emulation. Now coming to AI/ML usage in emulation or prototyping world. By prototyping, I mean FPGA prototyping, using off-the-shelf FPGAs. Uh, so I think there are different areas in emulation and prototyping where the EDA as well as the product companies are trying to invest and come up with mature solutions to leverage the AI/ML power and generate extract information from the huge amount of data that we have and then apply it back to speed up the things. For example, uh, as part of emulation or prototyping or basically FPGA model development, right? Uh, Whenever we are doing uh, a compilation, it is taking certain amount of hardware uh, capacity or number of FPGA modules, and then there is also the performance of the model that are critical factors. So if we can analyze the data for the different compiles and then come up with the optimal set of switches that can be used to provide us the best compile time, best capacity usage, and best performance, then that is one of the very critical use cases for AI/ML, learning and inference. Uh, since we are mapping the actual design on a hardware which also involves placement routing, whether we are doing it manually or we are taking help from the emulation software. uh, the emulation compile time again is a big function of how we are doing the partitioning and whether that is optimal or not, because if the partitions are too big and they are crossing across the FPGA boundaries, then there will be more time required to compile the design, as well as the performance of the model will be hit. So, what should be the optimal partitioning strategy? What That is another very important parameter. Uh, all these job synthesis, placement route, compilation. So these are very compute intensive jobs. So we need to ensure that we are giving the enough memory, enough cores, and using the right multi-threading parameters. Basically, the LSF grid settings has to be optimal to ensure that we are able to generate the optimal model. So these are some of the examples on the compilation side. Then on the runtime, you know, uh, unlike simulation world, we are probably limited in terms of the number of cycles that we can dump on emulator because it is running for millions of cycles as it is running very fast. So we need to ensure that if there is any issue, we need to identify the right window and then dump the waveforms for analysis in that window. So it is very critical that we identify that window of failure, uh, accurately. So this is another area where we are doing in-house development as well as working with EDA partners to come up with a solution, based on the regression failures. It can determine what should be the